without further ado, Alex, what is it? Sorry.
Okay, I already forgot what I said before. I remember I was somewhat apologetic. Now, so if you have forgotten what I said, let me quickly recap. So there are 80 slides. We're going to stop somewhere in the middle, hopefully around 45 slides. The stuff that will be out of those is very interesting, and that was actually how the whole subject developed. So I will be doing a revisionist version of history. But that's okay. In the age of fake news, that's fine. Jeremy Russell was a former student of mine. He is not far from here. He is in southern New Jersey. So here's the plan. In the beginning, we'll go over basic homological algebra, so basic that it is not mentioned anywhere. Well, that's not true. It is mentioned somewhere, but people don't read this. Now, this is the core concept of the whole talk, the stabilization of a functor. It resurfaces in many different contexts and with different names. Today we'll see the original. Many, did I say many? Well, I shouldn't be saying many. At least one more. Then we'll see a practical application in terms of the Auslander-Reiten formula. If you don't know what that formula is, don't worry. I will show it at some line in the slides, and then you can start thinking about it. That concept of stabilization of the tensor product, for example, leads us to what we call the asymptotic stabilization of the tensor product, and that was the original point of interest. I will explain that, why that was. The motivation here was to give a construction of Tate homology. Let me say more when we come to it. Now, and that would be it for today, I hope. There will be very interesting things afterwards, but they require a lecture of its own. So this concept allows you to redefine, give a new definition of the classical torsion. I'm not talking about a torsion theory, because what this defines is not a torsion theory. It's a radical, but it's not an important radical. It's going to be in the slides, so if you're interested, you can just read on after the lecture. Now, everybody knows that torsion has a historical prototype. It goes back 100 years ago, more than that actually, to the work of Poincaré. And that was a geometric notion, not an algebraic one. However, the next concept, this is new. There has been no classical prototype for core torsion. And you can see the word core torsion popping up everywhere, and I make a rather serious claim that none of those instances actually justify this name of core torsion. So this is the first definition of core torsion.
Sometimes with topologists I see places where they have standardized an X, which they say is really a cotorsion.
Yeah, they say that a module is core torsion, but when you define core torsion, you need to define a core radical. In other words, as is the case with torsion. If you have a module, you should be able to say what the torsion part of it is. Likewise, for the core torsion. If I give you a module, tell me what's the core torsion part of it. It's a quotient portion. It's not a subportion. Obviously, it should be. But there has been no definition of that sort. So people try to define core torsion modules, but they lack any justification. Okay. And finally, and that's where we have a very strong connection with model theory, it turns out that these concepts, torsion and core torsion, are in a beautiful duality. There are certain functors. There's a certain duality discovered by Auslander and independently by Gruson and Brussel and Jensen, which takes one into the other. And quite often you can go back. Okay, but again, the last three parts, I did not plan to discuss them today, but they are in the slides. Everything that I will say today, or just about everything, is in the three preprints and archives. Just type in my name if you have patience, and then you will see many references. I have few papers there. Well, let's go to homological kindergarten. So, all the functors that we're going to look at today will be from modules to abelian groups. Okay. And I will assume that all these functors will be additive. So they induce group homomorphisms on the morphisms. So how does homological algebra work? Well, given any module, you find a projective ancestor, that is a projective module mapping onto it. Then you go to the kernel and do the same thing with the kernel, and you keep doing it. And you get an exact sequence of this sort. Then you take an eraser and erase the letter M, and what's left will be a counters of projectives that is called the projective resolution of the module M. So this part, beginning with P0, P1, P2, etc., is called the projective resolution. Now, the remarkable fact about projective resolution is that any two projective resolutions of M are homotopy equivalent, which allows you to start building invariants of modules.
Can I just say one interesting historical fact?
Absolutely.
My thesis advisor, Alex Heller, who was a student of Sammy Eilenberg, told me that Sammy told him that the reason why Bourbaki never wrote on homological algebra is because they didn't like this. Any two projective, you couldn't say the projective resolution.
Yeah, a projective resolution.
Right. They didn't like this because there were too many projective resolutions or something that bothered them.
I have to tell you that I'm a big fan of Heller.
Ah.
I bumped into his paper on the loop space functor in representation theory. That really changed my thinking.
Could I ask to go take...
You don't have to ask...
Kindergarten -1. When we say modules here, we mean modules over rings, right?
Yes.
Okay, I just want to be clear.
Yeah.
That's the setting. Okay.
Yeah. Yeah. You can go to abelian categories. Of course, you need enough projectives.
If you want to go really pre-kindergarten, modules over commutative rings with the unit?
Sure.
Okay, I just want to make sure that we have to,
Yeah.
we're saying module, we all mean the same thing.
Yeah, absolutely. In fact, one of the byproducts of today's talk will be, and that's known. What I'm telling you today should have been done 50 or 60 years ago. And why this is not the case, why nobody did it 50 or 60 years ago, well, we can argue, we can guess. I express my own opinion, a guess in the abstract. We'll touch upon that a little later. But actually, you don't need projective resolutions in most cases. That's you can find a proof in Mitchell's book, but we'll come to that later. So any two projective resolutions of M are homotopy equivalent, so you can start applying additive functors. Different choice will give you a different complex, but the complex, additive functors preserve homotopy. Homotopy is an additive notion. So additive functors will preserve homotopy, so you will have homotopy equivalent complexes in the end. The homology groups will be the same, and so these derived functors, well, these homology groups, they are called the derived functors. They will be the same, regardless of which projective resolution you choose. And a similar argument applies when you take injective resolutions, if you have enough injectives. Just to go on the other side, erase the module M, that is called an injective resolution of the module. And again, any two injective resolutions are homotopy equivalent, and so you can play the same game. Apply an additive functor to a resolution. Rid of the homology groups, so you got your derived functors. Any questions so far? Okay, so what are the additive functors? Well, the first paragraph just repeats what I said. And in the end, we have, well, today's show is brought to you by the letters L and R. So, L, forget about the second line. Let's look at the first line only when the functor is called derived. If you start with the projective resolution, the homology groups will be called the left derived functors. If you go with the injective resolution, that's going to be called the right derived functors, the homology groups there. For the contravariant functor, the letters L and R are interchanged because you decide whether it's left or right after you have applied the functor. Okay. Normally, you see that the left derived functors have subscripts and right derived functors have superscripts. But we deviate from the traditional notation. In the contravariant case, we flip the position. So if you see an unidentified subscript or superscript, don't panic. It's just an indication that the functor is contravariant. Okay. Well, this is the case of interest. The zeroth derived functor. If I haven't told you that, let me tell you now. This entire talk will never leave degree 0. An alternative title for this seminar talk could be Homological Algebra in Degree 0. All the concepts that we're going to see today, they're all related to degree 0 and only degree 0. Okay, so how does it work? Well, you see this functor f is being applied to the projectives P1, P0, and the homology, that is just the co-kernel by definition, because everything else is 0. So here's your zeroth derived functor, evaluated in the module M. But you still have this composition, weighted going this way and then to f of m. Where does it come from? Well, we have a map from P1 to P0 and then going to m. And the functor is additive. The original composition is 0, so this composition will be 0 also. And now you use what you teach your students. The universal property of the co-kernel gives you this natural transformation from the zeroth derived functor to the functor itself. And there's only one such transformation that makes this triangle commute. That's just the universal property of co-kernels. Here's an interesting fact. No matter what functor f you start with, the zeroth left derived functor will automatically be right exact. Straight from the definition. It's a very simple diagram chase. Regardless of f. As soon as f is additive, and we'll always assume that, L naught f will be right exact. What does it mean? It means it preserves co-kernels. And then we have a corollary that this lambda is an isomorphism if and only if the functor f is right exact. That's what how they brainwash you in homological algebra textbooks. So you take a right exact functor, tensor product, yeah, take the left and right functor because it's right exact. So torus 0 is tensor product. So why is that? Well, if it's an isomorphism, because L naught F is right exact, then F will be right exact. And if F is right exact, well, then this slanted arrow, well, what will that be? Well, that's the co-kernel. If it's right exact, it preserves co-kernels, and M is the co-kernel of P naught, P1 to P naught. So you're talking about the natural transformation between two co-kernels. It must be an isomorphism. So that's all basic. I'm sorry if I disappoint you. I'm telling you basic things that should be taught to undergraduates. And a similar argument applies to right-derived functors. The zeroth right-derived functor is always left exact. That means it preserves co-kernels. And as a consequence, you see that the natural transformation from the functor to its zeroth right-derived functor is an isomorphism if and only if the functor is left exact. That's the case with the home functors. Well, so let's summarize what we have here. So in case of the left-derived functors, we have natural transformation from the left-derived functor to the functor, here and there. And in case of the right-derived functors, we have natural transformations from the functor to the right-derived functor, here and there. Okay. And this repeats what I said a minute ago about these transformations being isomorphisms. So, and then you can ask me, why is the case I equals 0 so interesting? Oh, forget somebody. Why is it interesting at all? The short answer to this is that because all these arrows are universal. So the lambdas, they're universal with respect. I will draw a diagram in a second on the next slide. First, let me say it in words, or read it in words. So the transformations from the left, zeroth left-derived functor to the functor, they are universal with respect to transformations to F from right exact functors. Remember, L naught is right exact. Okay. And a similar statement is true for the right-derived functors. So these are universal with respect to transformation from F to left exact functors. So here's the picture. So here's your transformation from the zeroth left-derived functor to F. This is a right exact functor. Pick any right exact functor, rex here, and take any natural transformation to F. There will be a unique natural transformation into the zeroth left-derived functor of F, making this diagram commute. In other words, any natural transformation from a right exact functor lifts over lambda sub F. So in the language of categories, that tells me that the subcategory of right exact functors is co-reflective in the category of all additive functors. So, said differently, the embedding iota is this tiny letter here, iota, that embeds right exact functors into all additive functors, has a right adjoint, and that L naught. So, which gives you an interesting characterization. So, what is...
It's too bad that the nomenclature gets mixed here. But anyway, right exact and co-reflexive.
I know.
Right exact should be left exact. Too late. To change
You know,
that.
well, this, your remark may explain my remark in a moment. So what is this lambda? Forget about subscript f. So we have a natural transformation from L0 to the identity functor here. So lambda is a co-reflector. Okay, it's a co-reflector. Now just think about it. So why do we need projectives then to define L0? If it's the value of the co-reflector on your functor. Well, what if, well, just think about this possibility. The subcategory of right exact functors is co-reflective. And it's a theorem.
Maybe adjunct functor theorem might help.
Yeah, that's right. And it's a theorem. I don't know who proved it first. I read about it in Mitchell's book,
Here, Fred.
category. Try. Maybe it's in Gabriel's thesis. No? I read it in Mitchell's book. Well, you probably know this, I didn't. What Mitchell calls co-reflective is reflective, and what is reflective is co-reflective. If I knew that, well, I could have saved myself some self-esteem. But, all right. Similarly, we have a universal property of the rows. So the category of the subcategory of left exact functors is reflective in the category of well additive functors, and row serves as the reflector. So what is R0? R0 is the reflector. So what's the right exact functor? It's the value. What's the zeroth right derived functor? It's the value of the reflector on the functor. So the theorem that I think I wanted to mention, but I didn't mention, is that any functor on a small abelian category has a zeroth derived functor, left or right. So you do not need projectives on small categories. Take the category of sheaves, coherent sheaves, on projective spaces, for example. You don't have projectives, but you can still play this game. And in a moment, we'll come to the concept of projective stabilization. It applies, no projectives, but you can stabilize projectively. So I will explain it. Here's another intrinsic characterization of those lambdas. It turns out, and that's a complete triviality, that this natural transformation from the left exact functor to f, to the functor itself, is an isomorphism of projectives. The reason is this homotopy invariance of projective resolution. So when you start with a projective module, you just take that same module that's a projective resolution. That's it. So apply the functor to an isomorphism, you still get an isomorphism. All right. So then, what is that lambda f? It's the unique natural transformation from a right exact functor that evaluates to an isomorphism on projectives. We know the uniqueness by, well, let me not go into this way. If you have a map from a right exact functor, it lifts uniquely to if it's an isomorphism on projective, that lifting will be an isomorphism. So uniqueness comes for free from previous arguments. And again, we have a companion statement for covariant functors or contravariant functors. If you go from covariant to contravariant, replace projectives with objectives and vice versa. So this transformation from F to R0 F is unique in the sense that you know it if you know that it evaluates to an isomorphism on injectives. In the covariant case, and projectives, in the contravariant case. Well, here's an interesting consequence of this. If this evaluates to an isomorphism on projectives, well, let's take derived functors of this and derived functor of that. So we're applying Li to this natural transformation. That's an isomorphism on projectives. So you will get an isomorphism of this derived functor of L dot F and Li of F. And you have a companion statement for a covariant functor. Going from F to the zeroth right derived functor evaluates an isomorphism on injectives. So when you take the derived functors, the right derived functors of the, you will, that's applying your functor to the projectives, but this natural transformation evaluates an isomorphism of injectives. This evaluates to an isomorphism on injectives. Now this prompted Eilenberg to insert that opinion that the derived functors, he writes, are only the right derived functors are only interested for those which are left exact, and the left exact functors are only interested for functors which are right exact. And he quotes this argument, this one and that one. Formally speaking, it's correct. There's nothing wrong with this statement of the facts. But the conclusion is questionable, because this presupposes that you know something about L not F. But what that argument does is that it tells you it's okay to only work with the left exact or right exact functors. And that is not true. That's what I'm trying to show today. Formally, it is correct, but in practice, we will see that if you start asking questions about L node and R node, you get interesting answers. Eilenberg didn't like, it appears he didn't like the zeroth derived functors, and I think I have a proof. We'll go to the theorems of Eilenberg and Watts. I'll try and convince you. Let's do examples. So I'm going to look at the zeroth left derived functor of the covariant home. The right derived functor is known. That's home is home. That's it. My question about what is the zeroth left derived functor of the functor home? I don't think people know what that is. But in the case when this covariant argument, contravariant argument, sorry, is finitely generated, yeah, we do know the answer. So what is it? Well, look at this natural transformation. The star here means home into the ring. We have a module. We have a module of a ring. You can take at all, look at all linear forms. A star, that's the notation. And by the way, if you look up any book on differential geometry, probably 90% of them will have this kind of transformation. That's usually done in the context of vector spaces. So what do? If you have a linear form here, and you have a vector elsewhere, what can you do? Well, if you give me an element in A, evaluate your linear form, and use the scalar to scale the other vector elsewhere. That's the map. Now this map, what is this map? Well, look, on lambda, what happens? That gives you A star, and that gives you A star. You expect that's going to be an isomorphism, and it is, of course. It's the canonical isomorphism. So it evaluates to an isomorphism on lambda. But if A is finitely generated, then you can take the direct sums from this position out. And so that means this will be an isomorphism on free modules as well. Because free modules are direct sums of lambda. And then it will be an isomorphism on projectives. So what do we have here? We have a right exact functor and a transformation which is an isomorphism on projectives. That's it. We know what that is. It's L naught, right? The universal property. So, and if you know L naught, then you know all other LIs. L naught is the tensor product, A star blank, and the derived functors, left derived functor of the tensor product are torus. So here's the next thing you can take home today. The derived functor of home is tor. So when you run out of topics for conversation at a party, you can say, by the way, do you know what the derived functor of the home functor is? And when they say, yes, it's X. No, it's tor. Well, here's another example. We're going to look at the right derived functor, the tensor product. Again, deriving on the wrong side. Again, I don't know what that is in the general case, but when A is finally presented, we have a similar map. Again, you can play with the linear forms and vectors, and where else can you see? Differential geometry? Well, I'm not sure.
Well, in fact, basically what started category theory,
Yeah,
the first example with the forms,
with the forms.
was
Oh,
when
yeah.
it started Eilenberg,
That's right.
played invent category theory.
That's right. But definitely, you can find this in any course in linear algebra,
Sure.
or multilinear algebra, let's put it this way. Okay. So, on injectives, why is that? Well, that requires some proof, but it's not that complicated. Essentially, we have a double-decker diagram, and you use the exactness of home into an injective. So let's not worry about this. It's not difficult. And so what does it say? This identifies, well, if it's an isomorphism on injectives, and this is left exact, you know that's the zeroth right derived functor by the uniqueness property. So the zeroth right derived functor of the tensor product is home, and the high derived functors are x's. So after several drinks, you can say, no, no, you're wrong. The derived functor of the tensor product is x. Okay. How much time do we have?
At least a half hour, at least 45 minutes. So you want, we can go till 8:30, whatever.
Well,
We have attention deficit.
Well, these examples can be treated from a more general perspective, and actually in more than one way. Here's one possible approach. Whenever you have an additive covariant functor, you always have a natural transformation of this sort. You evaluate the functor on the ring, and take the tensor product with the result. And it's very much in the spirit of previous examples. Look, how would you go? Suppose you have an element, the vector in M, that gives you a homomorphism from lambda to M, which sends 1 to that distinguished element, small m. It's a homomorphism. Apply the functor. So you will get f of that homomorphism. And now if you have an element in f of lambda, just take its image, and you will be in f of m. So that's the map. Okay, so we are sort of 50% done in the sense that we have a natural transformation from a right exact functor to f. If we knew that creature commutes with coproducts, we would be done. Because that transformation evaluates an isomorphism on lambda. It will give you the canonical isomorphism. And to go to arbitrary projectives, you need the preservation of coproducts, because an arbitrary free module is the direct sum of lambdas, and then you go to the direct sum end. Okay, so that in the case when f commutes with coproducts, we have identified the zeroth left derived functor of f as f of lambda tens of lambda. Now, by the way, that applies to the example with the left direct functor of the home functor. And now we recover the theorems, the theorem, I should say, of Eilenberg and Watts. If you assume in addition that f is right exact, that's it, you know, then f and L naught of f is the same thing, but we have just identified L naught of f as f of lambda tens of lambda. So that's a recognition principle for the tensor product. But Eilenberg published a paper. Everything that I have told you up to this point was well known 16 years ago. So why didn't Eilenberg prove this? My only theory is that he didn't like the zeros derived functor. He just didn't make the connection between this argument and the properties of the zeros derived functors. Well, you can play a similar game for a contravariant functor. I don't want to bother you with this notation and these maps. It's pretty much the same idea. What actually is at play here is the adjunction between the tensor product and the home. That's what's behind. And then this way we recover the second theorem of Eilenberg. If you know that the contravariant functor converts coproducts into products and is left exact, then that's home. So it's just pretty much the same argument as before. Again, using the universal properties of the zeros derived functors. Okay, so I remind you that we're still in homological kindergarten. So that was my first point I wanted to make today, is that completely elementary arguments could have proven this in the late 50s or early 60s. Okay. And now we come to the concept of the stabilization of an additive functor. So to this end, let me first give a definition and then I'll have the picture. So we assume that we have an additive covariant functor, say on left modules. So what do? We're going to look at the natural transformation from the functor zeros derived functor and take its kernel. And that's called the injective stabilization. Why is it called the injective stabilization? Well, I think we should thank Heller for this. Because this rho is, and I should have had rho sub f here, I apologize. Because this is an isomorphism on injectives, this functor vanishes on injectives. And of course, when you look at the category modular injectives, well, that's called injectively stable categories, and I think the terminology is due to Heller. And that's how you get those functors that vanish on injectives. Anything can be gotten this way. So what do you know about f up bar? Well, it's automatically additive because it's a functor of an additive functor. So we're still in the category of additive functors. How do you compute it? Well, you saw the letter R naught there, and you think, oh, that refers to the zeroth homology. So in the zeroth homology, I need to know an injective in degree 0 and injective in degree 1. Turns out to be redundant. You can do it with one injective only. So here's a very simple way of computing the injective stabilization. Suppose you want to compute it on the module B. Embed B into an injective container, anything you like. As long as it is an injective and contains B, that would. Then you apply your functor to this embedding, and then take the kernel. That's it. It's a very simple way of computing the injective stabilization. So here's the defining sequence. I told you I'm going to stay in degree 0. Yes, we're going from F to R naught F. Nothing changes. Everything is happening in degree 0. Well, what is the injective stabilization of the tensor product? Let's try and see what that is. Well, here's the functor. A is fixed. It's just a label. And here we have a placeholder where we're going to put B in there. So because A is fixed, we call it inert, and because B, well, we need to do something with it. We need to take an injective container, we'll call it active. And then we have that strange harpoon notation. Well, it points to the active variable. Otherwise, originally we didn't have the harpoon, we had overbar, and that was very confusing. So the difference can be seen from this simple example. Let's talk about the Abelian groups. So the ring is Z. So let's fix Z, and let's take an injective resolution of Q mod Z. Well, that's Q mod Z itself. So remember, this is an injective container. Q mod Z is its own injective container. That's an isomorphism. Apply a functor to it. You still get an isomorphism. What's the kernel? The kernel is 0. So this injective stabilization of the tensor product will be 0. But if you try to do it the other way around, now you fix Q mod Z, now you take Z and take its injective resolution. Well, it embeds into Q. And now you tensor this injective resolution, well, you apply your functor. That's tensoring with Q mod Z. And Q to tensor Q mod Z is 0. So the and Z tensor Q mod Z is Q mod Z. So the kernel will be Q mod Z. So you see, you have extreme differences when you flip the direction of the harpoon. So it's not a balanced thing. Okay, so the harpoon always points to the active variable. Well, for finally presented modules, Auslander and Bridger computed that value. The TH here stands for the transpose. So here A is a finally presented module. So what does that mean? When we take the projective resolution, the first two terms can be taken to be finally generated. For an assume that F P naught and P1. Say this is given. If these are free, then this map is just given by a finite matrix. Now let's apply the functor blank into the ring. It's left exact, so we end up with this sequence. The dual of A, going to the dual of P naught star, and going to the dual of P1 star, and the core kernel of this map is only transpose. So what is a transpose? Essentially, it's a transposition of the matrix. If this matrix was M, then the matrix here would be exactly the transpose. That's the definition. It's extremely important in Auslander-Reiten theory. You can call it the mother of all dualities. When you apply the transposition twice, you get back to the matrix. All right? So here's an interesting character. Let's evaluate this injective stabilization on the ring itself. So we have a special name for it, S of A. Jumping ahead, beyond this talk, that's the torsion. The torsion. In the classical case, it coincides with the classical torsion, but it also coincides with something else in the finally presented case. Anyway, well, let's try and compute the projective stabilization of the covariant Hom functor. Well, turns out it's a very simple calculation. That's going to be Hom modulo projectives, right here. This underline here indicates that you take just the usual group of homomorphisms and mod out all those homomorphisms that can be factored through projective modules. That's called Hom modulo projectives. So this construct goes back to Ekman and Hilton, so early 50s. And that one topic was developed also by Heller. Ekman and Hilton were working on duality and homotopy theory. And they approached this task as engineers. They decided to build a prototype. And for the prototype, they took, of all things, prototypes for topological space, they took modules. Continuous maps were replaced by homomorphisms. What is the, when do you call two maps homotopic? If and only if they difference factors through a projective. So this necessitates a passage to the category of modular projectives. It's a wonderful theory, a wonderful category. It's very interesting, very useful. We'll see more uses of it in a moment. So it turns out that the projective stabilization of the covariant Hom functor is just Hom modulo projectives. Now, when you try to compute the projective stabilization of the contravariant functor, well, lo and behold, it's Hom modulo injectives. Yeah, it sounds crazy, but that's how it is. So this allows us to introduce a new character, which we call Q. It's a quotient function of the identity functor. What is it? Well, we just evaluate this in lambda. So it's lambda into B modulo injectives.
And that becomes cotorsion?
And that is our definition of cotorsion. So here's the summary. How do you projectively stabilize a functor? Don't think in terms of resolutions. You will get confused in no time. Here's the thing. I told you, all these errors between functors and the zero-zero functors are universal. These are units and co-units of adjunctions. So to take a projective stabilization, you take the co-kernel of the co-unit and take the injective stabilization of the functor. You take the kernel of the unit. Can't be simpler and more natural. Okay, so the letters, well, I just put those letters in there, so now you can see it. An extension of the Auslander-Reiten formula. I don't want to spend much time on it because I'm running out of time, I see. And so we work, lambda is an algebra of a commutative ring R, could be the absolute case. In other words, lambda could be any ring and R could be just Z. So any ring is a Z algebra. So take any injective inside, by that I mean any injective over that commutative ring R. And well, for brevity, let's have D sub J to denote the homing into this injective over that smaller ring R. Well, here's that formula. It takes the injective stabilization of the tensor product and turns it into the projective stabilization of the contravariant Hom functor. So here I wrote down all the details, why it coincides with the classical Auslander-Reiten formula when the A is finitely presented, but our formula does not require finite presentation. It holds for arbitrary modules, or arbitrary rings. It's a very general statement. Well, specializing to B being lambda, what this says is that the dual, well, think of this as a character module. The character module of the torsion becomes the cotorsion of the character module. That's how it reads. But let me, well, that's going to be the last topic for today. Asymptotic stabilization. That's how the whole thing started. John Tate came up with his cohomology theory for finite groups. I think it was in his thesis around 1950. So what he did, he noticed that if you have a resolution of the trivial module, so G was a finite group. K, well, it could be a field, or Z. So you look at K as a trivial module, we take a projective resolution, and then you dualize it into the group ring. So what happens is that you get a co-resolution, and it will co-resolve K. But then you can splice these two complexes and you get a doubly infinite exact complex of projectives. It's homologically trivial, but it's not homotopically trivial. This is not a contractible complex. If you have an exact complex of projectives bottom on the right, it splits. It's contractible. Homotopically trivial. But such things exist. And that means you can place, instead of the usual resolution in homological order, you can take this projective resolution. And the resulting cohomology theory will be spread out over the entire variety of indices from minus infinity to plus infinity. So in particular, you get infinite dimension shifts. So that also tells you that this cohomology theory is like to finite length phenomena. If you have an object of finite homological dimension, because of this infinite dimension shift, it kills that object. So you dispose of objects of finite chronological dimension, and you only look at sort of the steady state homology. In this case, actually, you have the steady state already on the level of resolutions. And then associated with this comes the steady state homology. That's the state homology. Cohomology, I should say. But then in the 80s, after several generalizations into groups of finite virtual cohomological dimension, that's a beautiful mathematics, by the way. That's what I'm touching upon here, and generalization of this construct. This is absolutely remarkable. So the generalization by Farrell. And then in the mid-80s, in all those things, the existence of this complete resolution, and by the way, that's already in Cartan and Eilenberg, is understood as some kind of a very compacted way of describing a duality. And for a long time, people thought that Tate cohomology requires a duality. And now we go into the 80s. So V stands for Pierre Vogel, a French topologist, who managed to construct this, an extension of this cohomology without any assumption on the ring, on the module. He still did it for finite groups, or for groups in general, without realizing that that actually works for all rings and all modules. It's absolutely beautiful mathematics. And then Buchweitz, about the same time, came up with another construction. And then in the 90s, Mislin and his student came up with another construction using the technology of satellites. So what we were left was a sort of gaping hole. So this is Vogel cohomology, this is Vogel homology. This is Mislin's construction, that's this student's construction. We have the Buchweitz construction, but there was no analog for homology. So I asked Jeremy to fill that gap. So, and Jeremy, well, so why should there be a homological? Oh, what could it be? Well, let's look at the Buchweitz construction. It's absolutely beautiful. And here comes Heller again. How did Buchweitz came up with this idea? Well, he knew about Heller's definition of a category with suspension. So the category modular projectives has a remarkable property. When you go to the first syzygy module, and that's the kernel of the projection. So if you have M, and you have a projective mapping onto it, the kernel of that is denoted by omega M. I would not be surprised if it was Heller who first had this idea. The idea being that omega it's not an accident here. So this behaves similar to the loop space functor in topology. And in fact, that paper of Heller that was titled On the Loop Space Functor in Representation Theory. Okay, so what is it? It's not a functor actually. But if you go to the category of modular projectives, it becomes a functor.
Why does it fail to be a functor?
It doesn't preserve composition.
So what is it? It's an applicative. What's it named? Sorry, I'm sorry.
Omega, this is called the syzygy module.
Okay.
The first syzygy module. Yeah, you should look at this. It has the largest number
Constants.
of this, what's it called?
Constant.
Treatise or what? C, Z, G.
Yes.
All right.
Descenders thing?
Jung talks about it.
Yeah.
So, yeah.
What's the obstruction to it being a functor?
Uh,
I mean,
Yeah, well,
if it is
you just asked me a favorite question. Yeah, I can talk about this category for hours. Here, you can make it into a functor in a very crazy way. You can go to canonical resolutions. You have a module. For every element, take a vector.
Yeah.
Take a frame module, mapping onto it, and then continue. So you get a canonical resolution. In this case, omega becomes a functor.
Wait. But then you must have the theorem about the differences when you choose different vectors.
Well, here the problem is that with this choice, omega will not be an additive functor.
Thank you. Okay.
Yeah, it took me quite a long time to realize that.
Thanks. Yeah, that's pretty serious.
If somebody told me that when I was learning logical algebra, that would have saved me a lot of time and self-esteem again.
Okay.
So, but if this becomes a functor on the category modular projectives, let's just iterate it. So Buchweitz starts with Mn, Mn, modular projectives, applies the functor again, etc. And then he takes the colimit. And that's Tate cohomology in degree 0. And if you need other degrees, you can just put an extra shift into this K or into that K. No, minus sign, doesn't matter. A beautiful construction. This construction is actually defines a universal inversion of n in the functor. So,
Kind of resembles stable things in spheres.
well, exactly. That's the definition of stable homotopy.
Yeah.
So Buchweitz maybe went one step further because he actually defined it as a category.
Yeah.
Well, in topology, if you go from the stable constructions to all possible indices, then I guess you get what's called the spectrum. All right? And, well, again, I'm running out of time. I wish I could show you this. It's very simple. It's a one-line solution. Is there a universal inversion of an endofunctor? Any category, any endofunctor, you can invert it universally. What you see here is the construction of the morphism spaces. This colimit gives you the morphisms in the desired category. So we're talking about categories with endofunctors, and an obvious notion of morphism between such categories. And then you're just missing the density. So you add formal symbols, omega to the power minus n. That's all. Works beautifully. Essentially, you don't need two lines. You can make it in one line. It's incredibly simple and beautiful. Well, at this point, Jeremy stepped in. He was much more conceptual than I was. He said, wait a minute. You know what that really is? This is not homological projectives. That is the value of the projective stabilization of the covariant Hom functor evaluated on omega kn. I was happy with homological projectives. Jeremy saw that that was the projective stabilization. I forgot to tell you that this construction works so well that if you start with an additive category and an additive endofunctor, the result will still be an additive category with an additive endofunctor. Of course, this additive endofunctor will be just a shift. That's why it becomes invisible. Okay, and now very quickly. So how do you go from stable cohomology to stable homology? You replace Hom with the tensor product. Projective stabilization should be replaced with injective stabilization. Omega will be replaced with the sigma. Omega on the inert size will be replaced with omega on the inert size. This way, you know what you're looking at. You need to have a sequence with these terms. Sigma stands for cosyzygy in an injective resolution. The only thing we're missing are maps.
So intuitively thought of like a suspension with the choice of letter.
Well, you do this simultaneously. You go to the loop space and you do the suspension.
Right. But now you have a purely algebraic analog of it.
Yes.
Yes, what is the algebraic suspension?
Well, you can think of this as the cosyzygy model. So you look at the M, take an injective container, and then this would be your suspension. That's it. Again, this is not a mathematical definition of suspension. It's more like an intuitive tool.
No, but it's very nice to see if this has a purely algebraic analog.
But that's what Ekman and Hilton did. Yeah. Chapter 13 of Hilton's book on duality and homotopy theory goes over this.
Okay, that's what I was going to ask you the reference.
Yes. Hilton wrote extensively on several papers on this subject. So that chapter 13, duality and homotopy theory by Hilton.
So this is where that thing you said with the module, let's see what happens for modules.
Yes. Well, the book came later because the papers came before.
Sure, of course. Okay.
Yeah, but actually the latter part, building the maps, becomes trivial. So what you need to do is, well, you have both omega sequence for one argument and the sigma sequence for the other. Let's just tensor them. And then look at the connecting homomorphism. And that's what gives you the maps immediately. So simple. And that defines the homology. Analog of Tate homology. So this is the homological counterpart to Buchweitz's construction. Here we come to an interesting observation. We have a natural comparison between Vogel homology and our homology. It's always onto, but it's not necessarily an isomorphism, whatever that Vogel homology is. Well, the problem is that that homology that we produce does not have long exact sequences. And that's, well, actually, there's a whole diagram here which compares Maestling's construction with Thor and our construction with asymptotic stabilization. They are identical, actually. There's an isomorphism. And then, of course, we have these comparison maps. They are onto. Well, at this point, and this will be my last slide, I guess. So the comparison maps. I knew about the similar situation before. I knew that Čech homology did not have long exact sequences. Yet topologists are very fond of it because it behaves better than, say, singular homology. Singular homology does not necessarily vanish in degrees above the dimension of the space. Čech homology does. And so the topologists gave a lot of effort trying to improve this notion. And this was done by Steenrod in 1940 and then by Sitnikov in the Soviet Union in 1951. So that became known as the Steenrod-Sitnikov homology, and I knew that there was a comparison map between the two. And it was onto in each degree. And I also knew that the kernel of that was given by a derived limit. So I made a conjecture that the kernel of our comparison map should also be a derived limit. And a few months ago I learned that this is true. It's Emmanuel and his student Martsinkovsky, who then worked with the Mislins construction. They proved that the kernel is indeed the derived limit. And with this, let me stop. Sorry for going over time.
No. Any questions?
We've been asking them in the songs.
I couldn't follow any of them. I'm sorry.
I was saying we've been asking them in passing, so.
Yes.
Oh.
Up to a certain point, I could follow a little bit, I think, and then I couldn't follow. Now, there's a very famous limit theorem, which seems to take something that's very small with two endpoints and lift it, and you seem to get all the other higher correlations. It's called central limit theorem. This has nothing to do with it. But
It's an interesting, well, yeah.
I mean, in other words, you have a distribution on the real, say, probability distribution, and then you take sums, and under mild hypotheses, in the limit you can't see anything except the expectation and the covariance.
Yes, there's now active work on applications of this central limit theorem and representation theory. It started by the work of Virchow and Karov already back in the 70s.
Yes.
Generally normalized.
Yeah, well, I was thinking, because you started out with this little tiny thing, and then I thought maybe that would be the limit, but it's not, it's something else. It's a shift.
Well, these limits, I would like to understand them. This has not been done, unfortunately, and there are so many questions. One of the questions is that, is there a topological way of actually reproducing these results? Another student of mine is working on that. Since we have such a remarkable parallelism between algebra and topology, so the idea is to actually use a topological construction of all the functors involved and see if the Steenrod-Sitnikov homology will be gotten. Or the other way around, Vogel homology will be gotten as the Steenrod-Sitnikov homology.
Anyways, I think we should thank our speaker again.
Thank you.
Well, thank you very much.